properties of logarithms in section 4.4. And let me see if you can help me finish this out just to get started. A to the y equals x. What's that equivalent to in terms of logarithms? What's that interchangeable with? It means the same thing as what? Anyone?
Log base a of x equals y.
Perfect, thank you. So log base a of x equals y. Remember, these have an inverse relationship. The logarithm is the inverse of the exponential function, and the exponential function is the inverse of a log. So it's not surprising that, the properties of logs are going to somewhat mirror or relate to properties of exponents. For instance, when you multiply two things with the same base, what happens with their exponents? What do? Add them. Yeah, a to the n plus m. Likewise, when you have the product of the log of a product, you can split that up as the sum of the logs. So somewhat similar, you're multiplying here, you're adding here, multiplying, adding. Likewise, when you divide, what happens when you divide things of the same base? What do you do with their exponents? Yeah, you subtract. And the log of a quotient is the difference of the logs. Now, I don't have a really good one that I like for this last one, but these are a couple of your rules. So for logarithms, you have the product rule, the quotient rule, and the power rule. I sometimes think of this as the parachute rule. This exponent kind of parachutes out in front, lands out in front, and multiplies the logarithm. Now these are your basic properties. There's a few other properties that kind of are around that are good to know. So if you have log base b of 1, that's always going to be 0. Log base b of b is 1, so those are a couple default ones. More generally speaking, log base b of b to the x is x. These two operations cancel each other out because they're inverses. It'd just be like taking the cube root of 5 cubed. Once you cube 5, you get 125, but then you take the cube root and you get back to where you started. That's because cubing and cube root are inverse functions. Same thing's happening here. You got the log base b of b to some power. That's just going to give you the power. You're doing opposite or inverse functions. Likewise down here. This is the change of base formula. If you're stuck with an older TI graphing calculator, say like an 83, then that's how you would change base to do logarithms. I'll give you an example. So let's say log base 6 of 1296. Okay, well, let's see what that is. Now, if you can't do this directly because you don't have the right commands and buttons on your calculator, then you can put it in this way. You could do that as, that's the log of 1296 divided by the log of 6. You've got to be careful to make sure you get a division sign underneath that. So let's take a look. Clear this out. Log of 1296 divided by log of 6, and bam. Oops, I did 1294. I should have done 1296. I was looking at that going, wait a minute, I expected something to work out nice and even. There we go. Should get a nice even 4 on that one. So if you have to, then that's one way you can work with logarithms if you don't have that key on your calculator. Let's see. You might be asked to fill out something like this in the homework, in which case log base 3 of 14, what would that equal? Well, WebAssign is kind of working you through that. It's asking you for a 14 here and a 3 here. So there'd be your log base 3 of 14. Now, you can prove to yourself that you got these things right. So to prove that I got something like that right, let me remind you that you can rewrite these things in terms of exponents. So first of all, let's calculate this, not necessarily with the quotient of logarithms like the problem is suggesting, but we'll just do it this way. Log base 3 of 14 should be something between 2 and 3, right? Because 3 to the second power is 9, 3 to the third power is 27. So there you go. So we get about 2.402 equals 2.402, and let's see, 2.402, dot, 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 dot. How can I rewrite this using exponents? Log base 3 of 14 equals 2.402. What would that look like using exponents? What to what power equals what?
3 to the 2.402 power equals 14.
Nice. 3 to this power equals this. Now, I should really put a little dot, 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 because this is going to go on forever. But 3 to the 2.402 dot, dot, dot should equal 14. Let's check that on our calculator, and we can check it with the answer key. So I don't want to type this number into my calculator. So what I'll do is I'll do 3 raised to the power of this number. And that number is stored in a little place down here called answer. If you hit the second key, then the opposite key, it's going to take the full precision of this number and put it in as your exponent. You should get exactly 14. Sweet. So nice little trick there. But our goal in this section is really not necessarily to spend time with the change of base formula. It's to get comfortable with these different logarithms, these properties of logarithms. So it's a combination of things. Now the purpose of this section is not really to make you compress or decompress these functions into one or into many. It's really to get you ready for the stuff that we're going to need in section 4.5. When we start solving exponential and logarithmic equations, that's when you're going to need this. So this is just a skill building section to get you ready for section 4.5. Now, I have kind of my own way of solving these things. Typically speaking, if I want to combine this into a logarithmic term, then what I want to do is I want to start using these rules from the right-hand side perspective and moving over to the left-hand side. First things first, let's get that 3 out from out in front, and I'm going to move that up into the exponent. So it's going to give me the log of x cubed plus a log of y. And let's do something else here. I'm going to take that negative 1 and put it up in the exponent. So I'll have the log of z to the negative first power. So, okay, looking good there. Now, the nice thing here is I've got the sum of logarithmic terms. So I can bring all those terms together. The sum of the logs becomes the log of a product. So here's a nice shortcut for you. The reason I got rid of that negative is because all these things are added now, and all of them have a coefficient of 1. So this is going to equal the log of x cubed times y times z to the negative first power. Nice. Now WebAssign will accept this. There's nothing wrong with it. From the point of view of an exam, I'd probably ask that you do one more little thing, and that's get rid of the negative exponent. How can I get rid of the negative exponent in something like this? Any suggestions? Yeah, write it as 1 over z. In fact, let's just put it in the denominator altogether. That's going to be log of x cubed y over z to the first power. And there, we're all done. Nice. That's what I was looking for. Now, one of the things we did here is once we had the sum of logarithms, we brought it together as the log of a product. That's kind of a useful little skill. So let me try and reinforce that one with a little off-script example for this next one. So this is still maybe kind of part of example B. So let's write this with one logarithmic term. Let's see, let me zoom out a little bit. Sorry about that. Should have probably given myself a little bit more room. Let me rewrite it. So kind of like the last one, try and write this with one logarithmic term. No guffaws of laughter yet? Man, you gotta, oh, Charlie gets it. All right. All right. Enlighten your friends. Log of what? Yeah, log cabin. Come on, I had to wait all semester long for this joke. Give me a little love on that one. All right, thank you. All right, I appreciate that. But it's, it's just trying to reinforce the idea that when you have the sum of logarithmic terms, it becomes the log of the product. So that's the real big message there to take away from that. Let's work with a couple more here. This one looks like a good one. So let me do that here. Let's, again, this is still example B. 5 times the log base 2 of 4 plus 3 times the log base 2 of B minus 2 times the log base 2 of C. By the way, one of the things that's kind of a requirement for working with these things is that the bases all have to be the same. If they were different bases, you couldn't do as much as we're doing here. Now there's a couple ways we can work this thing, but let's start by looking at this. Maybe we can make our lives a little bit easier because I think these are nice friendly numbers. Log base 2 of 4. Somebody's got some stalking music here. I feel like Freddy Krueger's going to be coming out of the wall or someplace. All right. In any case, what power of 2 gives you 4? 2. Now, if you're not good at that, if you're not like, I'm just not really nippy with those numbers, you can take out your calculator and do that one. That's not a big deal. So this is going to be a nice 2. As far as the rest of these things is concerned, I want to get rid of the coefficients. So I'll write this as log base 2 of B cubed plus log base 2 of C to the negative second. So what am I doing? I'm using our power rule in kind of the opposite direction. That comes up here as an exponent. That comes up here as an exponent. So looking better. I can bring these two terms together. Gabby, what's that going to look like if I bring these two terms together? You don't have to simplify it, just bring them together.
Log base 2 C or B times C?
B cubed.
Still have cubed? Okay.
B cubed C to the negative second. Good, thank you. And let's keep going. Alex, there's one other thing that I'd probably want you to do on this one. What would that be?
Put the C in the denominator.
Yeah, let's put that C squared term in the denominator. So we'll end up with 10 plus log base 2 of B cubed over C squared. Nice. Done. There's a lot of ways, there's probably dozens of ways you could approach this problem, but I think that one's the easiest. Had you brought the 5 up here as an exponent, you'd have log base 2 of 4 to the 5th power. 4 to the 5th power would be 1,024, and then you could take the log base 2 of that and get 10. So, I think I saw a hand over here. No? All good? All right. Let's try another one. Eventually what I want to do is give you a bunch to sort out yourself using these properties of logs. Let's try this one. So 4 log base 7 of x plus 5 log base 7 of y minus 9 log base 7 of z. So let me copy that down here. So 4 log base 7 of x plus 5 log base 7 of z minus 9 log base 7 of, log base 7 of, no, I messed up. Should be a y, and this is a z. Y and a z. Okay, so try and pull that one together, kind of like what we did with the previous one. See what you can come up with on that. Like I said, if you're watching this at home, pause the video and try and solve it yourself. Okay, so my trick with all these things is to get rid of the exponents, or get rid of the coefficients, make them exponents. So that 4 is going to come up here, 5 is going to come up here, and the minus 9 is going to come up here as well. Now, if you do it different, that's fine. There's a lot of different ways you can do these things. If you had an instructor that made an impression on you and you're happy with what you're working with, that's fine. You don't have to do it my way. Now the last exponent here is going to be z to the negative 9th. But once we've got all these coefficients out of here, now I can combine that together. So this is going to become log base 7 of x to the 4th, y to the 5th, z to the negative 9th. Allison, what's my go-to step here? What am I going to finish up with?
Use a fraction to be log 7, x to the 4th times y to the 5th over z to the 9th.
Perfect. This one, because it has a negative exponent, it's going to drop down. Sometimes you'll have two that drop down. Just going to depend on the problem. Now these properties only depend on the fact that they're logarithms. So that's going to include other things. For instance, this one. What's the base that's understood to be with log or ln, the natural log? E. Even though it's ln, it still has the same properties as log of any other base. So let's work on that one. We've got 3 ln of 2 plus 4 ln of x minus 1/2 ln of x plus 3. Tony, suggestions as to how I would start on this? Yes.
The leading coefficients of the exponent.
All right. Tony, do you agree with that?
Yeah.
All right. Good deal. Thank you, gentlemen. So we're going to move the leading coefficients to the exponents. So that's a good place to start. Because until you have a coefficient of 1 or negative 1, you're not really going to be able to use your properties of logs too much. So let's see. That's going to give me the ln of 2 cubed plus the ln of x to the fourth plus the ln of x plus 3 to the 1/2. So looking good there.
Negative 1/2.
Negative 1/2, thank you. Negative 1/2. Let's bring that together as the log of one term. So that's going to be the ln of, what's another way to write 2 cubed? 8, yep. 8 x to the fourth, and then x plus 3 to the negative 1/2. And finally get that last point by moving this x plus 3 to the negative 1/2 term to the denominator. That leaves me with 8x to the fourth in the numerator, and x plus 3 to the 1/2 in the denominator. You could also maybe impress me by writing something other than x plus 3 to the 1/2. What would that be? What's equivalent to x plus 3 to the 1/2?
The square root of x plus 3.
Yeah, square root of x plus 3. Remember, those things are interchangeable. Okay, let's try just a couple more with this. So we'll move on to example C. Are we okay with some of these earlier examples, A and B here? All right, let's try example C. And I'll do a couple from those. I want to get you guys working like we did the other day. So I am going to pass out some little packets that you can work on. Let's take a look at negative 1/2 log base 4 of 16. And there's a couple ways you can work on this one. Any suggestions as to how to start? What works for you? You should be easily able to find 2 different ways to approach this. What do you see when you're looking at this? Nicholas?
You move the negative 1/2.
All right. And what would that give me?
Log base 4 to 16 to negative 1/2.
Good. How would you want to simplify from there? Well, what's something to the negative 1/2 power going to look like? Well, I guess we can make our life a little bit easier if we get rid of the negative part of it, and it'd be 1 over 16 to the 1/2. Okay, not bad. Ben?
1 over 6, square root of 16 would be 1 over 4.
Yeah, so this is the log base 4 of 1 over 4. Without a calculator, what's the, yeah, go ahead, Ben.
Negative 1.
Negative 1. Nice. What about an alternate way to do that? And thank you, gentlemen. What's a different way I could do that one? Anything else?
Well,
Yeah?
You could simplify log base 4 of 16 to 2, and then multiply that by 1/2, negative 1/2.
So the question is, what power of 4 gives me 16? And the answer is 2. And you get negative 1. I think I like that one better. Oh, it's up to you. Both of them get you the correct answer, so it's up to you. Let's try the last one here. The ln of e to the e to the 100. Now, if you actually tried to just put this in your calculator would choke. This number is bigger than what your calculator can hold. By the way, do you know how big of a number your calculator can hold? It's just underneath a Google. Notice I spelled it differently. That was the original spelling. There was a mathematician who was looking for a name for 10 to the 100th power. And he asked his nephew, he says, what should I call it? And his nephew just stammered out, a Google. And he thought about it, it's like, okay. And that name stuck. So when, what's his name, Larry Page and his other partner, when they started Google, They intentionally misspelled it, but their thinking was that they have a Google amount of things that you can search for on Google. This is a huge number. The number of atoms, protons, neutrons, and things like that in the universe is thought to be around the order of 10 to the 80th. So, huge. In any case, let's look at this one. And we're going to have to solve this one kind of slowly in a little bit of parts. So, let's do this. Does anyone see anything I can do to simplify this just to get started? Does any of our rules apply? How about, that's an exponent, right?
Yeah.
Okay, that's cool. So it's going to be the ln of e to the 100 times the ln of e. And I think I mentioned last time that a lot of times you'll see me writing this not with the ln but with the base. What base goes with ln? E. So this is log base e of e. This is log base e of all this. But start from the inside out. In fact, this is one of our rules here that we have on our sheet. What power of e gives me e? Got one voice on that. Jaden? How is this going to simplify? What power of e gives me e? Yeah. This is just a 1. Yay. So what do we end up with here? Well, we end up with the log base e. Thanks, Jaden. Log base e of e to the 100. Do I really need to put the times 1 here? Times 1 is not going to change anything, so I'll just leave that off. Can you simplify that any further?
Is it just 100?
Yeah. Keep in mind that what we have here are a couple examples of some of our extra bonus properties. So the log base b of b, when your base and the argument match, then you're going to get a log of 1. Or if you have the log base b of b to some power, you're just going to get that power. Those two operations are going to cancel each other out. So we really used 5 and 6 from the front side of our handout. This is just going to be 100. Nice. Okay, let's work on some of these properties in the reverse direction. So we've built things up, now we're going to tear things down. Both sets of properties reflect skills that I want you to have. So, let's see here. I'm going to start out with this last one here and work from right to left. Let's see, that'd be so we'll start out with log base 7 of 5x squared over y cubed. Now we're going to use our product rule, our quotient rule, and our power rule as much as we can to try and simplify these things. One quick caution here, I can't start out by using my power rule because the exponents here only apply to these specific terms and doesn't apply to the whole thing in general. So I can't start by moving the 2 out in front or the 3 out in front. Got to be a little bit more thoughtful than that. How can I start? Which one of my rules does apply? Yeah, the quotient rule. So this is going to be log of the numerator 5x squared minus log of the denominator. All right, so that's a good start. Ryan, what can I do next?
You bring the exponents down in front of the log? Or is it?
I can do that here. So I can use my power rule here. So it's going to be minus 3 log base 7 of y. I can't do it here because the 2 only applies to the x. If the 2 was on the outside of this over here, then I could do it, but that's not where it is. So yeah, I'm kind of out of luck on that one. But there is something I can do here. Do you see what that is? What property applies there? Move this down a little bit. Is there any of these 3 that apply there? Product rule, yeah, the product rule. This is a product, so it becomes the log of 7, log base 7 of 5, plus the log base 7 of x squared. Is that okay, Ryan? Good, thank you. Almost done. Get that last point. Turn that A minus into an A. What's it going to look like? What else can I do?
Remove the square from the x in front of the log?
Yeah. So, I know it's called the power rule, but I always think of it as the parachute rule. This guy's just going to jump out front, like that. So yeah, and that's pretty much all that we can do. Log base 7 of 5 plus 2 log base 7 of x minus 3 log base 7 of y. Nice. Done. Let's try another one. Let's move over to the left a little bit. Log base, well actually it doesn't have a base there. So if it doesn't have a base, what base is understood to be here? 10. So that's your common logarithm, log base 10. Let's work on that. So the log of y to the 9th over the square root of 5x. Adrian, where do you think we should start? What rule can we use to get going here? So your choices are the ones that are on our handout. Product rule, quotient rule, and power rule. Do any of those look like they apply? Yeah, the quotient rule. You got something divided by something else. So nice. We'll start there. Thank you so much. Log of y to the 9th minus log of square root of 5x. Now what? Oh, did I give you the property for the logarithm of the square root? Did I give that to you? Oh, that's because there isn't one. Yeah. Sorry, there's a couple disappointed looks. I know, it wasn't nice. But there is something we can do here. You just got to rewrite it. How can I rewrite log of the square root of 5x? Yeah, so log of 5x to the 1/2. Now Ryan, this time the 1/2 applies to the whole thing. So unlike our last one where the x had an exponent of a 2, I couldn't take out the 2 there until I split it up. Here I can take out the 1/2. So do you see there's a little subtle difference there, but it's important. You good with that?
Yeah.
All right, thank you. So let's take out the 1/2. And at the same time, I guess I can get rid of the 9 as well. So that's going to be 9 times the log of y minus 1/2 times log of 5x. Looking good there. And then, let's think. 9 log of y minus, I want to see what you think here first, 1/2. What rule can I use here? Product rule. 1/2 log of 5 plus log of x.
So the one that just goes with one of them?
Ah, good catch. I didn't think anyone was going to get that fast. Let me put a little box around this. Some brackets. You can use parentheses, it doesn't matter. Sometimes I like one versus the other. But that negative 1/2 has to distribute itself to both terms. So the way I wrote it initially, without the brackets here, was wrong. And you're going to lose a point. And it's not that I enjoy taking away that point, but you do have to be careful about it. You can write it one of two ways. You can either keep it in brackets or parentheses like this, or you can distribute it. Doesn't matter to me which one you do, just as long as you're careful with that 1/2 and this term. So maybe take a second in your notes and write a little star, right here, to be careful with that, and realize that that's a little something that I like to test.
On the test, if we were to leave it as log of 5x, would that be marked down?
Yeah, because I'm going to want you to keep on going until you can't apply the product rule, quotient rule, or power rule anymore. So, yeah, you get a fair amount of credit for getting down here, absolutely. But can you go a little bit further? Yes. And what happened to? Oh, shoot. Okay. Good question. Anything else on this one? All right. Let's do a couple more here to finish off. Let's have some fun for a second. I just want your thoughts, and you can discuss amongst yourself real quick. Are these equations true or false? You take a look. I'll turn to your neighbor, see if your neighbor agrees with you. True or false on all these? Or some combination of true and false.
The last one. But that makes me think the first one. I don't like the first one. It could be.
Well, yeah, because it doesn't go with the
Yeah.
so, because none of them stay fractions. So maybe that one is off, but these
And then the other one.
okay. Yeah, the last one.
Yeah.
Okay. I'm curious to see how you guys do on this one. This first one, this is you can apply your quotient rule, right? And your quotient rule doesn't say this. It says that we should look at the difference of those two. So the first one is false. Did I forget to give you the log rule for differences?
No.
That's because this one is false as well. You can't distribute the log to there. It just doesn't work. As much as you might like it to work, it does not work. How about the last one? Got to do right on the last one, right? No, sorry, that one's false again. So, yeah. It's just not the way these things work. The only properties that actually work are the ones that are on this sheet. So, all right. I feel obligated to do these last two because especially one of those tends to show up on exams. It's not too bad as long as you take care with the exponents that you have to work with. So let's start with the one on the left, example E. Log of x times x squared plus 3 over square root of x squared minus 3. Any suggestions as to where to start? What rule can I use first? Somebody said it over here. Quotient rule. Thank you. So we use the quotient rule. All right. Let's see. Jess, what's it going to look like if I use the quotient rule? Log of what? Okay. Let's look at the quotient rule together then. The quotient rule says if you have the log of a quotient, that is the log of m divided by n, that you're going to take and subtract the logarithms, the log of the numerator minus the log of the denominator. Yeah, top minus the bottom, exactly. So this is going to be log of what? X times x squared plus 3 log of the square root of x squared minus 3. Nice. Let's keep it going. Neat.
The 9 in there?
So, oh, the base 9. Log base 9. Thank you. Thank you. Let's keep going. Neat. Is there anything I can do with this term here? Well, actually, it is factored already. We could distribute, but then we'd have to undistribute. We'd have to factor it out in order to proceed. So let's just work with it as is. Is there anything that I can do to simplify this?
Or to break it up.
Yeah, to break it up.
Break up the x from the x squared plus 3.
Yeah, this is your product rule. You've got an m and an n. So it's going to be log of m, or in this case an x, plus log base 9 of x squared plus 3. How about over here? What do you think I should do with this one? Am I just call it a day? Done with that one? Eric, suggestions?
I don't know what the actual break to the 1/2 power.
Yeah. Perfect. That's exactly what I was looking for. Raise it to the 1/2 power. Can someone help me finish this up then? What else is left? Yeah, that 1/2 is going to come out in front. So it's going to be log base 9 of x plus log base 9 of x squared plus 3 minus 1/2 log base 9 of x squared minus 3. Beautiful. Beautiful. Now, that's as far as you can go. There's no addition rule. I can't split this up as a log of this plus a log of this. There's no subtraction rule. I've used the product rule, the power rule, and the quotient rule. That's it. That's as far as I can go with this one. This one can inspire headaches, but it's not too bad if we actually kind of work it with exponents and work from the inside towards the outside. So let's start out with the inside. This is going to be the square root of x to the 5th times the square root of y. But is there a different way I could write the square root of z? How can I write the square root of z with, say, exponents? Yeah, to the 1/2 power. So, in fact, let me do this. Let me regard that as being a 2 out in front. just to remind ourselves that we're dealing with a square root there. If I was to convert this from something with radicals to something with exponents, that would be z to what power? The 5 comes up, the 2 comes underneath, z to the 5/2 power. That's your square root version, or your exponent version of the square root. Okay, let's keep going. Log of the square root of x to the 5th. And now I'm going to replace this y times z to the 5/2. And instead of the square root, I'm going to write it to the 1/2 power. So I'm slowly trying to get rid of all the square roots and replace them with exponents. That's going to mean for me in this next part, I'm going to have to remove the parentheses. What's going to happen with this exponent? Yeah, it's going to multiply each of the exponents on the inside. Even though there's not anything explicitly written here, it's understood to be a 1. So it's log of the square root of x to the 5th, y to the 1/2, z to the 5/4 power. Almost done. We got to do that one more time to get rid of all the square roots. So this is going to be x to the 5th, y to the 1/2, z to the 5/4, all raised to the 1/2 power. That last 1/2 is coming from converting the square root to an exponent. Whew. All right. So, last but not least, I want to rewrite that as log of what? What terms am I going to get in here?
Couldn't you move the 1/2 to the front?
Actually, you know what? That's a great idea. We could actually move the 1/2 to the front and then deal with that instead of multiply. Yeah, that's a great idea. So if we want to move the 1/2 to the front, then we don't have to worry about the multiplication anymore. There is one thing we are going to have to be more careful of, though. So let's equal 1/2 times log of x to the 5th, y to the 1/2, z to the 5/4. So that's a nice friendly approach to this. It does mean we're going to have to be a little bit more careful in one regard. I still need to use my product and power rules here. Let's start out with the product rule first. This is the log of a product, so it's going to be the sum of the logs. 1/2 log of x to the 5th plus log of y to the 1/2 plus log of z to the 5/4. What mistake am I making?
You need the bracket.
Yeah, you need those parentheses. Here and here, here and here. Almost done. There's one thing that you have to do left, and then the other one is optional. What's the have to do one? Brooks, any suggestions? What else is screaming out in this problem that we need to do? What other rule do I have here on this sheet that I can still use? Are there any quotients? Are there any products? Power rule. Yeah, thank you. So we'll use the power rule. That 5, the 1/2, and the 5/4. All those terms are going to come out in front. So I'll end up with 5 log of x plus 1/2 log of y plus 5/4 log of z. And that's right. You can leave it there, and I'll be really, really happy inside if you do. If I had continued and distributed this here, then it'd be like multiplying all these coefficients by the 1/2. So if we didn't do it the way Annalise suggested, then you would have ended up with 5/2 log of x plus 1/4 log of y plus 5/8 log of z. Okay, so, all right, looking good there. Either of these is acceptable. You have the 1/2 factored out or not, doesn't matter to me. Last but not least, I've got a couple different curves drawn here. Neither family of curves could actually be what we expect for, the logarithmic function for these bases. Let's try and remind ourselves as to why. So, okay, let me shut this off. So here's your graphs of logarithms. If you remember, your graphs of logarithms are inverse of your graphs of exponents. One of the important things I said about the graph of exponents is that they all have to pass through 0, 1. Now what's that going to mean in terms of your graph for logarithms? What's going to happen to your graph of logarithms? Yeah, they're going to have to pass through 1, 0. And if you look at the graphs here, they don't all pass through 1, 0, do they? No, so neither of these could be the family of curves that it purports to be. I mean, it's true that they all have the nice vertical asymptote at x equals 0, but yeah, none of these passes through, or they don't all pass through 0, 1. Need to pass through actually 1, 0. And they don't. All right. So I'm going to put you in groups and let you work on something that we started out the other day. Any other comments or questions on this one here? All right. Let's put this one in the books.